Welcome back in class of 12th Mathematics NCERT. Hello my dear students, I hope you are having a nice day. Our discussion is continue on continuity and differentiability. Lastly, we discussed the concept of continuity with some important examples available in NCERT book. In today's lecture, we will discuss a very important function that has infinite many discontinuity. Yes, I am discussing about greatest integer value function. This is one of the function which has infinitely many point of discontinuity. So today we will discuss how can we define greatest integer value function, what is its graph, how can we find its point of discontinuity, and what is the criteria, general criteria to show this function is discontinuous at every integral point. So let us start from its definition. Greatest integer value function. Integer value function. This function is actually piecewise function that has infinite parts. This is denoted by this bracket value. X is equal to bracket value of x, and it can be defined as this has a value 0 if your x lies between 0 and 1. This has a value 1 if your x lies between 1 and 2, where 1 is included in this interval and 2 is not. Its value is 2 if your x lies between 2 and 3. 3 is not included but 2 is, up to so on. And similarly, its value is -1 if your x lies between -1 less than x less than 0. Its value is -2 if your x lies between -2 and -1, up to so on. So actually this is the definition of greatest integer value function. This function is denoted by this bracket, and it has infinite many parts. So firstly, we discuss how can we find the bracket value of this function at some real number. For example, you want to evaluate the value of 0.25. How can you evaluate this value? There are the two ways. Firstly, you can use the definition of this function. You have to check in which part this number 0.25 lies. As 0.25 lies in this part where x is 0 to 1. Your x is 0.25. Clearly, your x lies between in this value 0 to 1. 0 to 1. 1 is not included. So 0.25 will be here between 0 to 1. Now in this interval, the value of the function is equal to 0. So the first way to evaluate the bracket value of 0.25 is you can directly use the definition, that is equal to 0. But in this way you have to see the definition of bracket value function. The alternative way, that is very simple. You have to find a greatest integer that is very nearly close to 0.25 but should be less than 0.25. You have to find a greatest integer which is nearly close to 0.25 but should be less than 0.25. So you now 0.0 is the greatest integer that is close to 0.25 and it is less than 0.25. So that's why its integral value, its bracket value is 0. We take some more example. Suppose you want to find the bracket value of pi. How will you evaluate? As pi is approximately 3.14. 3.14. So approximately 3.14. You have to check you have to find which is the greatest integer that is close to 3.14 but should be less than 3.14. 3 is the integer. 3 is the integer which is nearly close to 3.14 but it is always less than 3.14. So the bracket value of pi is 3. We take some more example for a negative real number. For example, I want to evaluate the bracket value of 1.5 minus 1.5. You have to find a greatest integer that is nearly close to 1.5 but should be less than 1.5. As you know, there are the two integers which are nearly close to 1.5. One is minus 1 and the second is minus 2. But we have to choose the smallest one. The smallest one is minus 2. So its value is minus 2. So this is the concept behind the greatest integer value function. In this way, you can find the bracket value of any number. Next we make its graph, and from its graph we will observe that this function is discontinuous and it has infinite many discontinuity. Okay. First we draw x-axis and y-axis. This is my x-axis, this is my origin, and this is my y-axis. And this is negative x, this is negative y. Now we locate all of these interval on the x-axis. The first interval is 0 to 1. 0 to 1, 0 is included but 1 is not included. And at this interval the value of the function is 0. So suppose this number is 1. So at this interval 0 to 1, the value of the function is y is equal to 0 here. As 1 is not included here, 1 is not the part of this interval, 1 is not a point in this interval. So I will draw here an empty circle. So this is the graph of the first part. This is the graph of first part that you can see here like this. This is the graph of first part where y is equal to 0. Next, in second part, our x lies between 1 to 2. Suppose this is our x is equal to 2 here. At this interval 1 to 2, the value of the function is 1. That is, the height of the function is 1. That is, the value of y is 1 here. Suppose this is y is equal to 1. Y is equal to 1. So in this interval, your graph will be like this. This will be a straight line. This will be a straight line. Always straight line. As 2 is not a part of this interval, so I will draw an empty circle here. and this is y is equal to 2. Y is equal to 1, y is equal to 2, y is equal to 3. These are always represent a constant function, and the graph of constant function is always a horizontal line. So you have to draw every time a horizontal line for each interval. Lastly, for this interval 2 to 3, the height of the function is 2 here. I have to write here y is equal to 1. This is my next point, x is equal to 3 here. And for this interval 2 to 3, the height of the function is y is equal to 2. So now the graph will be here, this. Because 3 is a not part of this interval, so I will draw an empty circle or a hole. This is represent y is equal to 2. Similarly, you can extend this graph more. For example, if you take one more point, x is equal to 4 here, then graph of the function for y is equal to 3 will be lies here. Y is equal to 4. Circle will be here on the right side. Now we take negative intervals. The first negative interval is -1 to 0, and for this interval the value of the function is y is equal to -1. Where we will locate y is equal to -1? Where does lies y is equal to -1? Y is equal to -1 lies here on the negative y. Y is equal to -1, and this is x is equal to -1. So when your x lies between -1 to 0, the value of the function is -1. So now your graph is here. Now your graph is here. Here. Now, is zero part of this interval? No. So I will draw an empty circle here. And further you can notice that you can also draw a solid circle for every point which is a part of this interval. So you can make a solid circle here, but this is not necessary. If you do not want, then you can leave this solid circle. It is understood that the other part is included here, but you have to show the empty circle compulsory. So next our interval is -2 to -1. For this value of the function is -2 here. This is y is equal to -2. Now our graph will be here. This is the solid part, and this is empty circle, that is the hole, and here y is equal to -2. Now from this graph you can observe that at every integral point your function is discontinuous. For a continuous function, you know the function graph has a no break. There are infinite many breaks in the graph of the function. There are many points where the function graph of the function has a jump. The first jump is here, the second jump is here, the third jump is here, up to so on. Similarly, there is jump here for the negative side. So from this graph, for every integral part, the graph of the function has a jump, has break. That's why you can observe that this function has a infinite many discontinuity. So in short, you can say that f of x is equal to bracket value of x, that is the greatest integer function, is discontinuous for all integral values of x, for all integral values of x, Are there values for which this function is continuous? Yes. For all values which are real but not integral, for those values this function is always continuous. For example, if you take any real number x between 0 to 1, that should not be integer. Mean to say, you cannot take 0 here. Any value that lies between 0 to 1 will always be a real number in the form of decimal. Your function is always continuous. In the first part, 0 to 1, this is the horizontal line, and this horizontal line is itself a continuous piece of this function. That is, that shows this is a continuous function in this interval. So we can write greatest integer function is continuous for all real x which are not integers. So this is very nice function. This function has infinite many discontinuity as well as it has a infinite many continuity. It is continuous for any real value of x which is not integer. It is discontinuous for every integral value of x. Next, we prove this all of this thing in general, because we have observed all of this value from its graph or from its function. Now we prove in a general way that this function is discontinuous at integral value, and it is continuous for all real x. Okay, here we will discuss the two cases to prove that this function is discontinuous. Case number 1. If x is equal to c is a real number other than integer. In this case, if you find either its left or right limit in both direction, its limit is limit x approaches to c, f of x is equal to limit x approaches to c bracket value of x, which is equal to bracket value of c. For example, just for elaboration for your convenience, say if I say my c is 0.25, if you move to the left of 0.25, that is, you find the left hand limit at x is equal to c is equal to minus 0.25. So 0.25 lies in this interval. If you move to the left of 0.25, your value is 0. Similarly, if you move to the right of 0.25, right of 0.25 means you have to choose a value which is very nearly close to 0.25 but should be greater than. Right of 0.25 doesn't mean you choose a value which is very far away from 0.25, like some person choose the value 25. This is not valid. Right of 0.25 means just a value. You have to pick a value which is very nearly close to 0.25. You can choose 0.30, 0.27, 0.35, etc. But in each case, when you choose a very nearly close value of 0.25, which is greater than 0.25, in every case your value of the function is 0. Value of the function is 0. So that's why I have written here the bracket value of in this function at x is equal to c, where c is my real number other than integer, is always the bracket value of c. So this is the first case. In the second case, if my x is equal to c is an integer, now it will have always two values. Case number 2. Case number 2. If x equal to c is an integer, now if you find its left and right limit, both will be different. Firstly, we evaluate its left hand limit. Limit x approaches to c negative f of x. Limit x approaches to c negative, my function is bracket value of x. This is equal to, how can we find the left hand limit at x is equal to c? I will elaborate this left hand and right hand limit by using a particular, just for your convenience, by taking a particular interval or any particular value of c. Suppose my integral value of c is, suppose this is 1. If you find the left hand limit at x is equal to c is equal to 1, in which part of this function x approaches to 1, but it is less than 1. This is this interval 0 to 1. In this part, the value of the function is 0. In this interval, our x is less than 1. And I have to calculate the left hand limit. Left hand limit means you have to choose that part of an interval in which x is nearly close to 1 but should be less than 1. So in this part, the value of the function is 0. Can I say that this is actually c minus 1? What is c? C is 1. 1 minus 1, this is 0. Now, if you evaluate its right hand limit at f of x, right hand limit at x is equal to 1. Right hand limit of f of x at x is equal to 1 mean you have to choose that part of the interval in which your x is greater than 1. See here, this is the interval in which your x is greater than 1. And in this interval, the value of the function is 1. Value of the function is 1. Can I say that this is equal to c? So this is logic. This is the key fact, that in case when you will evaluate the limit of the function, left hand limit of the function at every integer, its value will be simply equal to c minus 1. So this is c minus 1. And similarly, when you will evaluate a right hand limit of this function, this is simply equal to the real number, the integral integer c. Next we will write, as the left hand limit is c minus 1, this is not equal to c. That's why this function is not continuous at x is equal to c, where c is my integer. So finally we will say that our greatest integer value function is discontinuous for every integer, but it is continuous for every real number other than integer. So this is the short lecture in which I have discussed the concept of greatest integer value function graphically, numerically. If you find this video is helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care.